So welcome everybody. Till, can you confirm? Okay, no, this is not what I want. I want display setting, duplicate slideshow. This should work. And
Yep, looks good.
okay, thank you. Let me, can I make this? Okay. I think this should work. Okay. Aha, sorry for the delay. Welcome everybody to the second lecture on the Coming Up to Speed course 2024. Thank you all for coming. Both Zoom people and in-person people. Zoom people, then you said that you can hear me well. Phil, can you confirm again?
Yep, loud and clear, looks good.
Fantastic. Okie dokie, let's start. So the first thing that I want to do today is go over some of the things that we discussed. I'm going to ask some people to mute themselves. Hi, okay, there we go. Hello. Aha, so remember one of the important things we discussed last time, be nice to each other. We follow this code of conduct, and oh my goodness, we have brought things to write. Fantastic, thank you, Josh. Okay, so that is the first thing. Second thing, wanted to go over the resources that you have available. We're still having some technical difficulties with the forum. A million billion thanks to Kyle, who is working day and night to fix it. As soon as that happens, I'm going to send an email to all of you so that you can register and introduce yourself in there. We have added some new things to the GitHub repository. I suggest that you go and check them out. It's a bit more organized as well. I will show some examples in a second. And in the YouTube channel, I am putting the recordings. Let me get out of here. So this is how, okay. This is how the YouTube channel looks like. So if you go to the Ascension YouTube channel, I have organized it in a way that now talks and lecture notes and everything are in different places. So this is a recording from last week. You can see the discussions that we were having about derivatives and the in-class game and the charged potato. So if you have missed this class, there you go. You can watch it, or you can watch it later at your convenience if you need to review it. Also, Daniel and I recorded a second instance of the Python crash course. This was about importing packages and actually creating plots. We went over how you can define functions and create plots of those functions. And Daniel also took me in an adventure over some of the resources that are online that shows you how to plot many amazing things. And I spent a long time just amazed by this. So check that out as well if that is useful. Okay, in terms of the folder itself, I reorganized it in this way. We're going to have the slides and notes from the different classes. So if you click in here and you go to lecture 1, you will see the notes from the PDFs annotations that I was doing. These are not as useful if you don't have the video, but now you have both. And you have the slides, and I'm going to put these slides into lecture 2 as well when we have that. You have the playgrounds in where you can find the first playground and the second one that I just finished some minutes ago. We'll discuss that in details later. And you have the in-class activities. Whenever we start today's class activity, I will share the QR code so you can go in there. So this is the most important QR code that you should have. If you haven't take a picture of that yet, please do so now, because that's what we're using for the entire course. And that's where we are going to be putting the materials. Okay, now, as I'm going to put this summary there as well. It's just that I forgot to put it. This is a summary of the last class. I need to find a way of making this default. Okay, there we go. A summary of last class. We discussed an introduction to the course, and the most important aspects that I want to summarize from that is remember to be nice to each other. The forum, the GitHub, and the playground resources that you have for yourself and to play with others. We discussed calculus and why it's so important, not because it allows you to find tangents of curves or find the area under curves, but it's the main pillar of the science and technology that we have been able to develop for the last 300, 400 years. We talk about derivatives, and I don't see Jay here. Maybe he's still eating ice cream, but the idea of this image is to remind you of that little game that we played in where we were able to see the gradient of the distance function until he was able to find the ice cream reward treasure that was hidden in there. We haven't talked about vector calculus yet. That will come probably in 2 classes, but you were able to see the distance function gradient with your mind's eye. And so the derivatives allowed you to optimize and describe instantaneous changes in systems. We're going to be talking about differential equations today. And we talk about integrals, and the important thing behind the integrals is not to calculate the areas under curves, but rather is a tool that allows you to add an infinite number of small effects into a very big appreciable effect. And the game that we played was to calculate the volume of a cylinder. And I don't know if have anybody here, either in Zoom or in person, actually calculated the volume of the cylinder and compare with the picture. Was anybody brave enough? Josh did, but he was expected to. So did you get something that was matching?
I guesstimated.
Do you have the microphone?
So I guesstimated the dimensions of the little disc because I didn't know what they were.
Because I didn't give it to you?
Yeah, so what I guess seemed reasonable, I think I guessed like 4 centimeters or something.
Mhm.
It was kind of close, so.
Very good. We have those thingies in the theory area, so we could.
Yeah, but I just wanted to guess.
Perfect, perfect. And anybody on Zoom guessed? I think I mentioned what the dimensions were, but I didn't write them anywhere. Okay, you have some things to play with later if you're bored. So that is the important part. This is the connection concept slide that eventually I'm planning on making a book and printing these things so you can take them with you, so you can remember every awesome adventure that we had during this class. The final thing is to open the floor for any questions from last lecture and to share the playground that we had. So I'm going to start first by asking anybody was able to do either 1 or 3. 2 was not into the playground because we haven't been able to talk about Taylor series, but anybody was able to create a Riemann integrator, numerical integrator, a numerical derivator code in Python? Josh, you can unmute yourself anytime, buddy. I just wanted people to be muted while I was talking in case there is background noise. So go ahead.
Okay. Yeah, I did it. I posted on the forum last night, but I was able to resolve whatever issue I had with 1 and 2.
That is fantastic. So in terms of posting your solutions from the playground, I talked today with Kyle to figure out what is the best way of doing it. And we converge into, I'm going to create a separate GitHub repository that I'm going to give access to anybody that I have the emails. So if you include it, of course, and then you can upload your playground solutions in there and we can see the evolutions as things happen. Especially if you're able to do visual things, for example, for the integrator, you can post them like the visual part on the forum. We're working still on the forum. I think that you were able to register is weird. Some people are able, some people are not, but I will give you access to the GitHub repository later today when I create it. Anybody else wants to share anything with the playground? Anybody was able to listen to the podcast? Anybody from Zoom? Very well, of course, no pressure. As I say, these are suggestions to play with. I am going to estimate that among all the different playgrounds that I'm going to give you during this class, listening to this podcast is the most important one of all of them. I strongly, very much recommend that you take an ear to it. It's a really good thing to know, especially if you can hear it early on. It will help you suffer less throughout your career. Lauren, can you share the microphone with her? Sorry to make. I'm going to find out a better way of doing this. Oh. Oh. Really? No, well, that is a fantastic thing to know. Let's see, playgrounds. I mean, that's the first thing that happened with the photo. And if nobody tells me that it's not working,
This is Hidden Brain. I'm Shankar Vedantam.
No, that's okay. It might be that the whatever I put in the QR code didn't work, but you do have access to the folder. So can you repeat that, sorry? Weird. That might be your browser. Okay, we'll check it later. By the way, Teal, I see some questions and I'm sorry, somebody said that coding was troublesome. So my recommendation for that, both asking for help later on the forum once we have it running, but going over these introductions is the best thing that you can do. You're going to need coding as we advance, but you have a lot of time to catch up and get up to speed with that. So try to go over the 2 YouTube tutorials that we had in here. And then one thing that I can do is sit down with Daniel and create a video of me and him going over the playground one on how we will make the derivative numerical derivator, numerical integrator, and that might help as an example. I was saying, Teal, if you can manage questions on Zoom, because for me it's harder to check response and everything as I'm going through things. But if there is something that I need to address, just please interrupt me directly from whatever you read on the Zoom chat and let me know to address it. That sounds good?
Yeah, there's only one question from Enrique Torres. Said, how much do we miss from lecture 1? But I think you covered that by saying that the lecture was recorded and it's on YouTube. So yeah,
Perfect.
says it.
And I'm pasting the link. And don't worry about
Yep,
it.
there you go.
Both lectures are recorded. So if anything was extremely important from lecture 1 for what we're about to discuss, you can just watch that and watch the new lecture after that. Okay, any comments from the previous lecture that anybody wants to make?
Can I ask a question?
Please, go ahead.
So the GitHub code spaces, we can do Python, and I found that we can also compile C++ programs. Is there a way to do Fortran as well?
That sounds like a Kyle question. I have no idea. I know how to do Python and Mathematica. Maybe somebody else here knows how to do Fortran in code spaces? Okay, I will ask Kyle, Josh, and let you know.
Thank you.
But that's a very good question. Okie dokie, let me stop sharing here, and I'm going to start sharing on my tablet. So we can start having a party with Taylor series. All right. Okay, so this is what we have for today. We did the summary for last time. Now, let's talk about Taylor series. And I'm going to ask the same question that I asked last time. For those of you who have heard about Taylor series, why? What is the use on this thing? Why are we interested in this at all? Also, before we go on that, since I'm recording the things in YouTube, if you do not want to be seen in video in the YouTube channel, right now I'm talking directly to you, Josh, because you're the only person with the video. Make sure to mute your video. If you don't mind being my companion in there for the rest of eternity, it's an honor to have you there. I want to make the disclaimer. Okay, why are Taylor series useful? First of all, I think it's easier, at least for the people in the room. Have you heard of Taylor series before? I see many yeses. Lauren, have you? Okay. And I see, Josh, you probably have heard about Taylor series. Why are they used? Anybody has any idea? I see from Maya, she says approximations. I like that. What does Maya means? Maya can also talk for herself or continue typing. Spencer. If we have it around, yes. Thank you, Josh. This is a fantastic card.
What I understand specifically about Taylor series, they're an approximation of a function the closest you can get without evaluating the function at a singular point on, say, a graph. such as n plus one polynomial and NPA.
Okay, so as an approximation tool, what you're saying, which I agree, is something that allows you to transform knowledge that you have about a function in a location into extending that to different locations. So I like both things. Let's think it in terms of this way. Imagine that you have a very complicated function. You can take the microphone back. Thank you, Josh. You might have a very complicated function, and I'm going to start with the most complex function of all time. Sine of x. And you might say, Pablo, but wait a minute, what do you mean sine of x is complicated? Well, for us, it's not that much because we have computers and we can calculate things with computers. But if you were 100 or 150 years ago, and you're really interested in knowing how much the sine function value is here, what do? At, let's say, x equals 0.1. You're trying to evaluate that function there. You have no idea. You know the value of the function at 0. This one is trivial, it's 0. You know the derivative, you know the second derivative, and so forth. And you're really trying to make your way to extrapolate from the region that you know to the region that you do not. So that is one of the uses of Taylor series, is how you can use the knowledge that you have in a location to extrapolate to a different location. That is not only in terms of calculating numbers. So in this example that I'm putting, we're calculating the numbers. So I'm interested in trying to estimate sine of x equals 0.1. But you could have, for example, differential equations that we will discuss in a second, in where you have a bunch of different functions that are playing a role in your problem, and having them explicitly there makes your problem extremely hard. But if you can approximate here and there, as Maya is saying when she mentions approximations, that can make your problem easier. So how do we go around this? Anybody remembers the formula for a Taylor series? We're going to discuss the concept in a second. But if I am interested in approximating a function f at a location, around a location x, a, that is close to a, Taylor series for a function x, a function f around a. Anybody remembers the formula of this thing?
It's this.
Uh-huh.
It's the sum over all values n of the function f to the order derivative n evaluated at the point of interest divided by n factorial multiplied by the quantity x minus a to the n.
Okie dokie. Thank you, Josh. And I think I was able to copy everything that you recited. So this is Taylor series of f of x around, phone is ringing, second. Okay, around a. But why? So we have the formula, a lot of faults, me included when I first started seeing this. You just memorize the formula and apply it and span it. I am going to get the formula. We're going to make it very small, and we're going to put it here. Oop. And I want you to reason this with me. Suppose that we are really numerically interested in finding the value of sine, the function sine around 0.1. We know the value of sine around 0. Sine of 0 is equal to 0. So my question to you, if I were to say sine of 0.1 is approximately equal to, what is the best number that you can give me right now that you think is a good approximation for how much is the value of this function there? To make it even more obvious what I'm trying to do, let's make 0.1 sit around here. And what do you put? Purple. So this is 0.1, and this is f of 0.1. What is the best single number approximation that you could tell me? How much is the value of sine of 0.1? Somebody says 0, and a lot of people are saying yes. What about the folks here in the room? Do you agree with some people, or we're going to fight the some people? Is 0 the best approximation that you could give me for this? 0.1 is a better one, but you're thinking further ahead. Yes, I agree. But why are you thinking 0.1?
It's an alpha, it's approximated by alpha.
Because you're already doing a Taylor series. But if it was a single number, not thinking too much, if you look at this function from like very far away, it's between -1 and 1, and you don't distinguish the point 0.1 too much from the point in the center. So the best approximation within what I'm saying that you could do is just say that this is 0. Yours is better. We're going to get to that in a second. So basically, the idea of this is saying the best approximation that I can do in here is just evaluate my function at the same location that I had before. I'm expanding the sine function around 0. The best possible approximation that I could give for what it is outside of the value at 0 is whatever it was at 0, which in this case is 0, so it's a bit confusing. Okay, so now Anne is saying I can approximate sine of something by just that something. The reasoning behind that is just come in and zoom in your function, and as we discussed last week, we're going to look at the derivative of this thing, and you realize that the derivative of this function looks like a straight line, and truly, if you zoom enough, you cannot distinguish between sine of x and the function that is just x. Right? Everybody's following this? Somebody lost in time with me? So if you say, I'm going to approximate this by the function x, if I'm evaluating at 0.1, my function x is just going to return to me the value 0.1. So the next best possible approximation that I can add to this thing is the function 0.1. But if we want to be more accurate, you see that this straight line to the right, I should start decreasing the value of the brown curve, and to the left, I should start increasing the value of the brown curve. That's where the next Taylor term is going to appear, which is going to be an x cubed. So basically, the idea of this expansion is saying, let me put in here, this is delta x times the value of f prime at x equals a. Find out how much is the derivative of the function at that location, and multiply by how much you are deviating from the location that you were after. The next term, in this case, because sine function is an odd function, so it's not going to have a quadratic term, but basically will be the next order correction to this idea. How much the derivative itself is changing. That is what it's telling you. If, for example, this linear relationship started curving in this way, and both of them were curving up, that is the next term in the expansion that you want to make. So it's an improvable expansion that every term that you add, you're increasing the fidelity that you're using to approximate your function. Make sense? Have I lost anybody? Okay. So basically, this is what, oops. This expansion over here, I'm going to take it back, is saying, if I were to work the first term, this is equal to f of a, that is your first guess that you could make for the value of a function wherever we are, plus f prime of x, evaluated at x equals a, how much your thing is changing in comparison to changes in x times delta x. This delta x is x minus a plus f prime prime, the same thing evaluated at that location, times delta x squared. You end up obtaining this 2 factorial because what you want is that whenever you take derivatives of this approximation, the derivatives match the original derivative of your function. So if you were to take 2 derivatives of everything that I have on the right-hand side, see that this, with respect to x, this delta x squared will bring a 2, and then it will bring a 1 whenever you take the derivatives. That is going to cancel the 2 factorial that I have below. So basically the idea is write a polynomial expansion that perfectly matches all the derivatives of your function up to order n, evaluated at the location that you're making the expansion. Make sense? We're going to take a break in a little bit with the activity, so I'm not going to be monologuing by too much. But so I have two things that I want to say. The first one is, if you were to finish this approximation of sine, remember that we said we're going to go in this way. The next term should be f prime prime evaluated at x equals 0 divided by 2 factorial divided multiplied by delta x squared. The second derivative of sine, so I have sine of x prime, this is equal to cosine of x, sine prime prime of x is equal to minus sine of x. If I evaluate that at 0, I get 0. As we were saying, there is no quadratic term. So this goes to 0. The next term is going to be a cubic term that is going to be taking one more derivative of this. So it's going to be with a minus delta x cubed over 3 factorial. So if you wanted to estimate the value of sine, in this particular case, sine of 0.1 is approximate 0 plus 0.1 minus 0.1 cubed over 3 factorial plus other approximations that we're not doing. So yay! Now we know how to calculate the value of the sine function at 0.1. Spencer.
What is the double derivative cancel out again? And what is the double derivative cancel out again?
So because you're taking derivatives of your original function, do you agree with me that the derivative of sine of x is cosine? If you take a second derivative, the second derivative of sine is minus sine. And now you have to evaluate this function at x equals 0. So at x equals 0, sine of x is 0. So there's nothing proportional to a second derivative or a quadratic function in this Taylor expansion. It just dies. Make sense?
Yes.
Okay, very good. Thank you. So now I have a problem for you that is a bit more involved than the sine function, and perhaps that can be a homework, or somebody can just tell me how we will solve something like this. Let me put it in here. Imagine that for reasons you're working in an engineering problem, and oh no, all the computers in your workstation have stopped working. You have to solve this problem by hand. You need to find me an approximation of the root of this equation. What is the value of x that I can put in here that I get this to be equal to 0? Any ideas?
I have an idea.
Tell me, Josh.
Since it's transcendental, you could plot both mother functions over each other and the points where they intersect.
That sounds fantastic. For plotting, I need computers or a lot of time on my side to make the plotting. Is there an easier way to get around this? What do I do to solve this problem?
Taylor series.
But of course, Taylor series, because we're talking about Taylor series. But what exactly? Anne was going to say something. Could you get the microphone there? Thank you, Josh. So what do we do?
I'd say
You can put it further away from you. It's a good microphone.
it doesn't have speakers here. I'll just
Mhm.
I'd say we expand exponential.
We can expand the exponential function. What do we do? So if we approximate exponential of 3x, we're going to do a Taylor series in x. What is this approximate to?
Well, you expand it around 0 and 1 plus.
So if I approximate, and that is a very important thing. If I believe that the solution of this entire thing is going to be around 0, then I can do that. If the solution to this equation is going to be around x equals 35, probably expanding around 0 is not going to be a good idea. But I chose this example because the solution is around 0. So yes, we're going to expand this around 0, and then what do we obtain for this?
It's going to be 1 plus
1 plus 3x. And you know what? I'm just going to stop there. You could continue, but that is just going to make your life more annoying. So basically what I'm going to do is, with this definition, I'm going to grab this thing, and everywhere that I was seeing exponential of 3x, I'm just going to replace that by this approximation. So this is going to be -1 minus 3x. And now the equation that I have to solve is x squared minus 3x, this minus 1 with this plus 2 minus 1 is equal to 0. And this is a quadratic equation, and I can solve this. I have actually a formula for solving this thing. I'm not going to solve it exactly, but that is a point, that this type of approximation is what allows you to go from a problem that is completely unsolvable by hand to something that you can actually do. Give me just 1 second. There is a question. Could you explain why in physics we end up using Maclaurin more than series, than Taylor? What is a Maclaurin series? I always get confused with all these names. I guess that is just expanding the thing around 0.
Yes.
That I don't. I hate those names. I understand that people discover these things in different epochs, but I always think in terms of Taylor series for these things. And if you're evaluating that at 0, turns out it's the same thing that Maclaurin was thinking. Many of our problems, you have massaged the situation in such a way that the place that you care about is around 0, but there is nothing special about the number 0. And in the homework, I think there is a point in where you're supposed to take derivatives and Taylor series of a function that is not centered at 0. There is nothing special about it. I hope that helped. Spencer, you had a question? I will repeat it on the mic.
So where did you get 1 plus 3x from? Just the process of doing it.
Because so think of the exponential. What I'm trying to do, I have my exponential function that looks like this, and I'm trying to expand around 0. So the same type of reasoning that we did before. Exponential of 3x. If I'm expanding around x equals a, which in this case is equal to 0, what is the simplest value that you can tell me that this function should be around 0? 1. So that's where this one comes from, right? Now I need to multiply the derivative of the function times delta x. What is the derivative of this function? Numerical derivative, so the actual numerical value of derivative of this function at 0.
3x.
It will be 3,
Yeah.
the number 3. And then I multiply by x, because x is the difference between x and 0.
Okay.
So that's how I get it. Make sense?
Yes.
Okay, perfect. So this is the thing that I wanted to say. I think I'm going to switch now to the activity because I have been talking for almost half an hour. Before I do that, this is a connecting concept that I want all of you to have because I thought about this very hard with Josh. I want you to think that what we're doing when we do a Taylor series is we have our function and we're dropping a tiny ant. You will have a drawing of a cute ant later on the summary. This is my ant. My best description for an ant should have 6 legs. You're dropping an ant in the middle of the function and you're asking the ant, hey, from tiny there, how does the function looks like? So the first thing that the ant is going to tell you what is the value, how high the thing is, and then the first thing that the ant is going to see is just a linear approximation to how your function is changing. I cannot make too much sum out of that, but you see that for the ant, it's already difficult to see that the function curves. It's the exact same thing that happens to the people that believe that the Earth is flat. They only took the first expansion, the first piece of the expansion in the Taylor series. They forgot to add, the x squared that starts curving the Earth. So a lot of the flat Earth problems could be solved if you told them to continue the Taylor series expansion. I don't know if I'm going to get in trouble for saying these things. Anyways, let's switch now to the in-class activity. Let me put that in there. So come to the, should we do the class activity or should we break and then do the class activity? My amazing education team, what do you think?
How about let's just take a little longer for the class activity?
Okay. So we're going to take 7, 8 minutes of class activity plus break. And the class activity is class forms. Okay, so all of you should have access to the folder. I'm going to copy this for some people in a second. There you go. It's in the chat. And then for you here, this is the in-class activity QR code that we have in here. Basically, the idea is you're going to see the functions that we have in here on top. And we want you to find the first Taylor term and the second Taylor term in their expansion around 0. It's a graphical thing. So You just have to see it and click and plot it. And I strongly recommend that people in person try to find at least one partner that you're going to discuss this with as we go through it. And people on Zoom, eventually I'm going to make it work such that we can have breakout rooms and you can do the same. But for now, I strongly encourage you to type in the chat your reason. Since I want to stretch, I'm going to declare that we have a 3-minute break, and then we come back and we're going to be doing the activity. If you want to start the activity, you're free to do so, but I'm going to stretch in here. So okay, I want to make a clarification because that's a very good point. The things in purple that you see in here are after taking into account the value of the function at 0. So for example, if you look at cosine of x, the value of cosine of x at 0 is 1. And none of this function seems to be the value at 0 to be 1. And that is okay, because we are taking basically that is not being plotted in here because it will be very bold. It will be an horizontal line. So imagine that you have already taken into account the value of the function at the expansion location, and you want to do the next terms of the expansion. Does that help? Yep. Then next non-constant term. Yep. We have 1 more minute, and then I'm going to start talking. Very well, my friends. Sorry for interrupting the discussions, but we have to come back to it, or I will not be able to talk about differential equations. Josh, do you have the microphone around? Okie dokie, perfect. So let's start together discussing the first one, cosine of x. Any thoughts? What should be, so how should the function cosine of x behave around 0? What should be the first approximation level we can do? Equals 1. Very good. So the best value that you can say, if anybody asks you how much is cosine of a value around 0, you don't think. You immediately say 1. That's it. You want to refine that? That's what we're going to do for the next Taylor series, the next part of the Taylor series, but the first value should be 1. What about sine of x? What would be the best value to say? The value of sine of x should be around x equals 0. But scream it. 0. Very good. Fantastic. Thank you. What about this function, which for some reason it has a 5? I thought that we wanted it to be at 2, but that's okay. A 2 or minus 1? I don't remember.
2 looks like 5 or something, right?
Yeah, perfect. We're expanding around where, Josh, this one?
We are expanding around 0.
We're expanding around 0. Okay. So what should be the value of this function around 0? Somebody says 5, and somehow I don't think so. 6. 6 and 5 look very similar to each other. But yes, it should be around, it should be 6. So that is the first thing that you can say right after. Now, let's go back to cosine. After you have said that cosine looks like the function 1, constantly 1, around 0, what should be the next improvement that you can make? Do you see any linear term? Do you see anything that looks like a straight line in cosine around 0? If you were to really zoom in there. Let me put it in a different color. What does this remind you of? A parabola, right? X squared. If you actually make the Taylor series, you make 2 derivative of the cosine, you're going to get a non-zero term that is going to multiply an x squared. So a parabola. But I want you to get the graphical part. So for cosine of x, what should be the answer to its first non-zero, non-constant term among us? Of course, not this one. Not this one. This one looks like something that is not x squared. That looks more like x cubed. So probably not this one. So I'm left down with 3 things that look like parabolas. This one doesn't look like a parabola because it's kind of flat in the bottom. Actually, this is next to the 4th term. So between D and I, can I have anybody tell me which function should be? Josh.
Also for clarification as well, we are expanding 1 over 1 minus x thing around 2. So
Oh, around 2.
not around.
Not around 0. So that might change the value that we're after. But yes, you were expanding that around 2. So shouldn't it be I because evaluation around 0. And I agree. It's a parabola, but the height, the peak of the parabola should be at 0. If the peak of the parabola is somewhere else, this is not a good Taylor expansion for this function. It will not look like this function. So everybody agrees that the answer should be I. Unanimously, I see people agreeing the perfect. Yes. Okay. So now the question: what is the next order correction to sign? You see that this looks like a parabola, but what will happen if I plot the entire parabola? I'm going to get something that looks like this. Maybe a little bit less hairy if I plot it with a plotting program, but can you see that if I just continue my approximation, it's something that goes on bounds and goes down and crashes like Bitcoin, right? So how should the next term look like if I want to correct the correction that I have done? Anybody has any idea? Some people. Joshua, since I'm seeing you in video, you can also just dance in the way that you think that this should look like. Anybody has any ideas? Oh, I see Joshua, he's praying the sun. Praise the sun. Okay, so what Joshua is saying is, well, if somehow I could add a term that around here kicks in and starts making things go up, and around here also kicks in and start making things go up, I will be very happy because I will correct this thing that was going to crash. So I need a function that kicks in after a while, and after that while is pointing up. Any ideas? Let me erase everything from here. No, not that. That was unfortunate. Okay, how can I? Okay. So we already know that this is taken. Which ones from all of these? Any ideas on what should be the next expansion term? Some people help this time, so I need somebody from the audience in person. Which one of these looks like they are praising the sun? But which one from the graph? It looks like x to the 4th, I agree. But remember what we said, it has to be something that stays relatively constant and then starts praising the sun. So Anne says E. Do we agree with Anne? E, the x to the 4th term, Maggie says. Perfect, yes, that makes sense. So you see how easy it is to make Taylor series. You wouldn't even have to write an equation. You just have to match how the things look. And that is intuition that I want you to develop. Let's do one more. And after that, I'm switching over to do something else. Let's do sine of x. You already know how to do. Let's do this one. That seems complicated. We said around 2. So we're expanding around here. So when x is equal to 2, then f of 2 should be around how much? What is the first approximation to this thing? Anybody? Four-ish. If x is equal to 2, 1 minus 2 is minus 1. So it will be -1 in total. So that means 5 minus 1. So this should be equal to 4 plus something. Now, does this has a linear correction? If you put an and in there, can you see it? The problem is that my picture is awful. So let's take a picture that is better. The problem is that the plot is awful. Okay, so you know what? I'm going to make my output. So the function looks like this. It's coming from the infinity. And I start doing this. You cannot see, oh, how did that happen? That was very weird. Thank you. All right. Can you see my screen now? Of course, that's what. I'm sorry. Okay. I got it. So we're expanding around x equals 2. The value of this function here is 4. Do you see a linear term? Will an and see a linear term in there? Some folks, anybody has any idea? If I drop an and here, here's my cute and. Does the and see a linear term?
Yes.
Yes, but of course, yes. This is a linear, the and that lives in its ant world, the only thing that it sees is this as a first linear approximation, right? That's how the function looks if you're very, very tiny and you're standing in top of them. Everybody agrees. Okay, so my first non-trivial approximation for this thing should look like a straight line and a straight positive line. Anybody sees anything? I'm going to also take this out. What do you think? So I see f. I have f and g, both are straight lines, but it should be something that at the location that we're after, which is around 2, should be 0, because we're already taking into account the value from the other function. So yes, it should be f. That is the next function that I will have to add. Now, here's the question. What is an x correction for this part? So I need something that will preclude the ant from just walking ad infinitum up. So I need to have a function that drags this down and also drags this down, right? Can you think of a function that will look like that? Josh, do you want to dance again? Ah, so Josh is saying praise the, I guess, the court of the earth. Can we identify anything like that? This is also taken now. What should be the next expansion on this function? Fantastic. So I hear D. D looks like a sad parabola. It's doing exactly what we want, and it's centered around 2. So yes, the answer to this one is C. And you can see how, in this particular function, you're going to start correcting and correcting in ways that on the right is going to be very complicated, because the function should go to minus infinity very quickly. So you're going to have to add all of these terms, each one of which is going to be very important. And this relates to something that I don't have time to go into details because I really want to talk about differential equations. That is basically the radius of convergence. This function has a problem at x equals 1. You can see it here. This is a problem. If x is equal to 1, this entire thing blows up, which means whenever you make a Taylor series around 2, in this case, the Taylor series is going to converge between 1, not including 1, and 3. So a symmetric center around the number 2. And that has to do with properties of analyticity of functions. We can discuss that whenever we go to complex numbers. Okay, it's up to you to do the sign one. Now, let me see if I have one extra thing that I want to tell you, and then we can go to differential equations. Yes. My question to you, if you go and you do your homework, and you finish this expansion for sine of x, you're going to find the Taylor series that are the two terms that are basically left in here. You're going to find that sine of x, as we discussed before, is approximately x minus x cubed over 3 factorial. And if you go one more, plus x to the 5 over 5 factorial. That is the Taylor expansion of the sine function. I recommend that you try it at least once so you know. Here is my question. Josh, I'm sorry. You can see it if you're tired, or you can see it. All good on my side. Here's my question. If you were to plot this, and you will see this in the beautiful Taylor series online document that Josh and Daniel put together, where you can actually visualize the Taylor series of the sine function. If you were to plot this, and you plot your sine function, your true sine function, between minus pi and pi, this is your sine function. This is going to be the result of that expansion. So in red is my Taylor approximation, and in green is my true sine function. My question to you, is this the best polynomial approximation of degree 5 for the sine function in the interval minus pi to pi? Basically, can I put any other numbers in front of these x's that are not the numbers that you're seeing, aka 1 minus 1 over 3 factorial and plus 1 over 5 factorial? Can I put any other numbers in here that will make the red curve approximate the green function better? So Muhammad says no, ... Anybody else think something else? Well, think about it, because we're going to talk about that when we talk about projections. The answer is yes. Depending on what you say, better. If by better, I mean that the curve overall looks more like the green curve, the answer is a definite yes. And I'm going to blow your mind whenever we calculate those numbers because it's extremely cool. That is one of the things that you can use to merge linear algebra concepts of projections of vector spaces with calculus concepts. And it's very, very good. Okay, we have half an hour to talk about differential equations, so we better get to it. Let me stop in here. And I'm going to have, well, actually 20 minutes because I want to talk about the homework. So I'm going to have a 3-minute break. Everybody stretch, and then we're coming back. We're coming strong on differential equations. If anybody else is okay, 2:32. Let's go back to talk about differential equations. Aha. Remember that I said when we first started talking about these things last class that the two main things, in my view, of the uses of derivatives and derivatives was optimization problems and addressing differential equations. Why do we have differential equations in the world? The connecting concept that I want you to have is the rules of games. I want you to think of chess. For those of you that really like chess, and you have, somebody tells you all the pieces, you have the rook, and you have the horse, and you have the bishops, and the queen, and the king, and the pawns, and all of that. I want you to think of that, and I want you also to think of soccer, the true football, not handbag. So I have soccer. These are two very different games that have very different rules, are playing in very different ways. It's really hard to determine exactly how a particular game of soccer or of chess is going to is how a particular game is going to be played. If you were to tell me, I don't know, I am going to play chess against Frank, who's leaving right now because he has to go, it might be very hard for me to describe exactly what is going to happen on the game. But the rules of the game and what I expect instantaneously to happen are relatively easy to write. I can tell you the pawns and the different pieces move in this way. If I see that Frank is grabbing a specific horse or knight in the chessboard, and he's going to move it, and I see that there is only one spot that the horse can occupy at this time, I can tell you perfectly well what is about to instantaneously happen in this game. The same thing with soccer. It's really hard to explain how exactly the match of soccer is going to be played, but I can tell you instantaneously if a player has a ball or if the goalkeeper has the ball, the goalkeeper is about to kick off the ball in a specific way, is going to land more or less in this direction, etc., etc., etc. With physical systems, the same things happens in where we are able to write equations on how they change instantaneously, for example, with respect to time. And the examples that I had in here is bacteria and radioactivity, Newton and Schrödinger. I'm going to try to not dwell too much into it. Well, actually, if we don't finish today differential equations, I can always borrow time from the next class. We don't have any rush. I don't know why I'm rushing. Let's think of a Petri dish where I tell you that I have a bunch of bacteria, and I say that every X amount of time, let's say an hour, every hour population duplicates. Okay, so if I want to describe how the population of bacteria as a function of time in this Petri dish changes, I could tell you, well, an instantaneous change in the population, let's say the derivative of this thing with respect to time, is proportional to how much population I have at the moment times some constant lambda or tau. I could call that constant tau, and it tells me a characteristic frequency or time scale of the problem. I am very good at writing this equation. I'm not very good at telling you explicitly, and this is how the particular population is going to look as a function of time. I have to solve this differential equation to actually obtain that. The same thing happens with radioactive decay. In that case, instead of having a positive exponential growth, I put a minus sign in here, and see, I have changed the rules of the game slightly, just by a sign change, and now my system is going to evolve in a very different way. It's going to exponentially decay because in this case is talking about a sample of nuclei in a radioactive sample, and they are decaying, and as they decay, I have less and less. So the probability of observing a specific decay is less likely. So the population is going to decay in an exponential way. But other two equations that I wanted to mention, Newton's equations, whenever you say I have a physical system and you say F is equal MA vectors, and I prefer to write these equals to the derivative with respect to time of the momentum, because your mass could change. You could be describing a rocket. You're going to change the rules of the game of your system by changing what are the forces that are acting on your system. For example, if you have the Earth and you're trying to describe, as I say, a rocket that is moving around the Earth, then the rocket is attracted to gravity through the Earth, but also the moon is jumping around, so then the rocket might also feel attracted to the moon. You put all those forces in your system, you solve the differential equation, hopefully, if you have numerical techniques that allow you to do that, and you see how the system can evolve. But at the same time, you could use this to describe what is happening to a pendulum. You have a pendulum that is oscillating with respect to gravity, and you want to describe that by the angle that is making with respect to a perfectly vertical line. And the pendulum has a mass, and you know that it has the force of gravity that is acting towards down, and it has the force of the string, the tension that is acting up in the radial direction, and you're trying to see how the pendulum is going to evolve. You just put it in Newton's equation with the appropriate forces, and you're able to get how this thing evolves with respect to time. Make sense? Any questions with what I'm saying? Can everybody see this as changing the rules of the game will give you different evolutions of the system, and all of this ends up happening through differential equations? That is a mouthful of a question, but I see people saying yes. Zoom folks, are you following me? I see Joshua. Always nice to see you in person saying yes with your head. Thank you. The same thing happens with Schrodinger equation that we're going to, and I see Maya saying yes as well. With Schrodinger equation, we're going to analyze this in more detail later, but eventually you're going to have a system for your quantum system that is going to look like the Hamiltonian, which is an operator, a differential operator, applied on your wave function that is a function of x and time. And this is equal to I h bar. By the way, I had a minus sign in the previous lecture that was wrong. The derivative with respect to time of your function psi of x and t. Doesn't matter the details. This is just a thing that is describing the process in how your wave function of your system diffuses through time. This is a differential equation. Once again, you're going to change the rules of the game, aka what you put in this Hamiltonian, and you're going to be able to evolve the system in time and try to understand its properties. Any questions so far? Okay. So let's solve some differential equations. Before we solve differential equations, this is important that this is something that I want to share with you. The thing that I put it in my notes. I want to talk to you briefly about something that I call the level of problems. Basically, we're going to make a tower of how hard it is to solve something. And what I want to tell you is that the further down you go in this thing, the further you are into the depths of mathematical complexity, and things are becoming very, very hard to solve. The easiest things, all of this is moving my hands. Of course, I can find problems from tier 3 that are way easier to solve than some very hard problem from tier 1, but just for you to have an idea of why things happen. The easiest things to solve are normal equations. This is level 1 of this ladder. What is a normal equation? X squared minus 2x plus 1 is equal to 0. Where I'm trying to find a number. Trying to find what is a number that I put in here, then I get to solve. Make sense? The second easiest thing to solve are integrals. What does it mean to try to solve an integral? It means to try to say, for example, what is the function that, let me see one that is non-trivial. That when I make one derivative, I get sine squared. I want to integrate the function sine squared. So I need to find the antiderivative of sine square of x. I need to think a lot. Which function, if I were to make one derivative, I will get sine square as a result. Make sense? Problem 3, differential equations. Let me put in here ordinary differential equations. that looks like, for example, f prime of x is equal to lambda f of x. I'm not looking for a number anymore. I'm looking for a function. So, you know, it's more complicated. And the fourth problem is partial differential equations. Is when I'm trying to solve something that the function depends on two variables at a time. So, for example, df of x and y at dx is equal to 3y squared f of x y divided by x. I made this up. Don't try to solve it. This is much, much harder to solve than the things above. So the reason I'm going to be monologuing for 8 more minutes, and then we're going to have our final discussion, and then we're going to finish talking about differential equations next time. The reason why I'm presenting this is because every time that you are in any stage of this ladder and you can move up by doing anything, that is a win. You're going to see that there is going to be problems in where we're going to be here trying to solve an ordinary differential equation, and me or the textbook or your professors are going to come and tell you, aha, but if we do this particular trick, we can move this and that, and now we just have to integrate this function. And I remember when I was taking the classes, I was like, yeah, but I still have to integrate something. We haven't solved anything. Why are you so excited about having breaking these two variables in this way, and now we're able to integrate the function? I still don't know what it means. You move up one way in the ladder of complexity, and now it's a problem that is much more approachable or manageable to solve. The same if you have a partial differential equation, and somehow you can break that into several linear ordinary differential equations, then that is a win in my book. Make sense with this? All right. Perfect. So let me see the next thing that I want to say. By memory. So some of the equations, differential equations that I will love if you can just dedicate to your memory so that you can solve them anytime that somebody asks you that. The first one is, let's solve it together. F prime of x is equal to f of x. What is the solution to this? Anybody? Anyone else? It's not a rhetorical question. And so Anne says that f of x equals a times e to the x solves this problem, right? The a is important because I can multiply this function by any number and it will still be a solution to my differential equation. And e to the x because that is one of the most recurrent functions because it has a nice property that its derivative is related to itself. Yes? But Anne, are you ready for the next challenge that I'm going to make? What if I were to put a 3 in here? What is the solution to this? Somebody that is not Anne can answer. What is the new solution? Somebody from Zoom. What do I do now if I have a 3?
Put a 3 in the exponential.
I just put a 3 in the exponential. Thank you, Joshua from Zoom, right? Easy peasy. But what if I were to put a -3 in here? What do I do now? Now it doesn't work. Joshua, what do I do? Help.
Put a minus sign.
I put a minus sign in here. Fantastic. I'm very happy. Now, I'm going to make it really hard for you folks because you seem very, very smart. And I'm going to ask somebody that is neither Anne or Joshua to answer. Some of you have seen me already done this trick. I'm going to put a palm tree in here. I am very good at drawing palm trees. Look, these are the coconuts. So f prime is equal palm tree times f. What is the solution to this differential equation? Anybody but Joshua and Anne? Who knows? Lauren? The solution is palm tree. So f equals palm tree.
Well, a to the on here.
A to the E.
A,
very good. So you see, I don't need to redraw this thing. I just put it in here. We're going to raise this f in a second. The solution to this thing is going to be e to the palm tree x. And you will be saying, Pablo, but what the heck are you doing? Why are we wasting our time? Anne, you want to say that? Go for it.
No, I'm just asking, what if the palm tree is not a constant?
Oh, yeah, that's my point. The palm tree could be an operator. So, for example, the palm tree could be the Hamiltonian of my quantum mechanical system. So you know what? We haven't talked about quantum mechanics yet, but I think you all are ready to solve Schrodinger, the time-dependent Schrodinger equation. So what is the solution here? Let me help you a tiny bit. I'm going to move this IH, I'm going to put it dividing here. And you know, when you divide by I, it's the same as just multiplying by I. I'm putting a minus. I'm dividing by H bar. This is my equation. What is the solution to this differential equation then? Smart people.
You could assume it's product separable.
I don't need to. Yes and no. It's complicated. I don't want you to think that much because I haven't given you any details on this. But out of your gut feeling, looking at what is in the screen right now, what would you say should be the solution to this?
E to the negative IH over H bar. Sorry, that goes in the exponential, yeah.
E to the negative I H over H bar. What else?
With a T.
I need a T. Fantastic. Because you see in here, this was a function of X. And to clarify this, I should be writing this as d at dx. In here, I have a d at dt. So I'm going to put a t in here, time, because my derivative are with respect to time. But now I need a constant. So in principle, I could just borrow this a and put it in here. But I'm going to cheat. I'm going to put it here. And since the function that I have on the left is a function of x and time, I need something to depend on x. So I'm just going to put in here psi as a function of x at time equals 0. Because the equation, the differential equation, and this has to do with the separation of variables that you were mentioning, is only talking about derivative in time. The operation in x is a bit more complicated. We will address that later. This fellow here is called the evolution operator. And this is how we solve time-dependent problems in quantum mechanics, or at least this is one way. But I remember when I was the same height as you, and I was looking at the evolution operator in the Cohen-Tanucci quantum mechanics book, and I was so confused on how the heck are we doing e to the h. But if you have already done e to the Pond tree, you don't fear anything. You can do whatever the heck happens. And by the way, the solution to this is Taylor series. Eventually, we're going to expand the exponential into a Taylor series, and that's how we're going to be able to bring that h down in a way that we actually can act on my wave function side. There is a second differential equation that I want you to know by memory. F prime prime of x is equal to minus lambda squared f of x. Can anybody that is neither Anne or Lauren or Josh tell me what should be the solution to this second order differential equation? And after this, we're going to stop, and I'm not going to talk about numerical differential equations until next class. Anybody has any ideas? Can you tell me your name?
So my name's Colin.
Colin.
Yeah.
I will forget. I'm sorry, but eventually I will get it.
Don't worry about it.
Tell me.
It's gonna be something like a cosine omega t minus b.
So you say a cosine omega t minus phi.
Well, in this case, t to the x.
Oh, very good. Yep. And are you sure you want to put an omega in there?
Lambda.
Muy bien. Yes. So lambda. Yes, this is a solution to this differential equation. If you make two derivatives with respect to x of this thing, you get minus the thing that you got multiplied by lambda squared. Everybody sees that, or you want me to make the derivative? It's a part of your homework. I have other things that I need to say. Do it, and if you get confused, you can come back to that. Here's the important bit. You could also have written this as a cosine of lambda x plus b sine of lambda x. And that will still have work. Bye, friends that have to leave. We'll see you next time. Okay, I'm almost done. There is one thing that I want to say, that you could also have written this using the exponentials that we were describing before. You could have said, well, I'm going to write this as c times e to the I lambda x and b times e to the minus I lambda x. It's up to you, part of your homework, because you're not going to be able to do the homework that has to do with the differential equations, to convince yourself that this is the case. And that is because sines, cosines, and exponentials have some interesting relations. They're basically the same function in the complex plane. It's just that we like. Okay, so let me go back to our menu for today. We were able to do everything up to here. This is what we're going to discuss next time. I'm going to now share my screen on the playground that you have to do, that you can do for Wednesday. And I'm going to tackle questions that people may have. So let me see. So the playground for this week. Don't do part 3. You can try, but you don't have to do part 3. You can do part A and part B of part 2 because you now know how to, or at least the analytical part. And you can start reading about Euler's method if you want on how to numerically solve differential equations. We're going to address this on Wednesday. But the most important thing that I would like for you to do is to grab somebody in your family, friends, cats, dogs, anyone around you that is not familiar with Taylor series, and explain to them what a Taylor series is. That is part of your playground, which is not a home. That will be a fun activity to do, and you start gaining some experience and knowledge on how to connect ideas in creative ways once you try to explain it to them. With that, I would like to open the floor for questions about the class, the structure, the previous homework, what we have done today. Somebody in the chat was asking if I have any recommendations for the GRE. That is a problematic thing. I don't like those tests. What I suggest that we do is ask me that question in the forum once the forum is working, and I can put some resources and the strategy plan that I use at least to study for that. It was the worst time of my life, but that is okay. So, any questions or any comments before we finish today?
I have a question.
Please, go ahead.
So for problem 3 on this playground, do you want us to do, like, what level of write-up would you like us to do? Because I'm actually interested in knowing, once we get there and get into classes, what the expectation for, like, the level of write-up will be for professors in terms of, like, homeworks and stuff.
Well, I'm not grading anything, so I have 0 expectations. It's up to you to do whatever you want with these things. I don't know what is the exact expectations of professors here. What will make me extremely happy if I were to grade this, which I'm not going to, but I'm going to put them and be very proud of them in the GitHub repository and say, look at what the students of this class have done. So what will make me very happy is if you have a Jupyter notebook in where you say in LaTeX, these are my equations. You can put also a figure of the pendulum that I stole from Wikipedia, and you can steal it from there, and say, this is the differential equation that we want to solve. These are the approximations that I'm going to make. You can type that in LaTeX with markdowns in the Jupyter notebook. I will make sure to make a tutorial on how to do that with Daniel. And show by doing a Taylor expansion on the sine function, this is what we get. This is a solution to the differential equation that we get once we are there. And now I have a numerical integrator that solves this exactly or without making a Taylor series approximation. And the notebook ends with a very nice plot of the function as a function of time, the true function versus your Taylor approximated function made for 3 amplitudes. 2 in which the sine approximation works and 1 in where it doesn't. And you can clearly see how the actual numerical solution is deviating from your approximated solution. For me, that will be more than.
Okay, so, but you're not looking for, like, an analytic solution with an ansatz.
Well, if you make the approximation, the Taylor series, you should be able to solve that differential equation.
Okay.
You make a first order Taylor series expansion on the sine function. You will arrive at what your professors most likely told you in classical mechanics at the beginning undergrad of what is the solution to the pendulum problem in physics, but that is for small angle approximations. But I want you to be able to, with computers, show that that approximation can break.
Thank you.
That's it. Any more questions? Okay. with that, we are closing today's session. I will see you on Wednesday at the same time. We're going to finish differential equations and we're going to start with linear algebra. Vector matrices, we're going to discuss about eigenvectors. I'm going to bring a row. We're going to play with it. Thanks everybody, including some people, for coming, and I will see you in a couple of days. Bye.